Right now, as you read these words, a star 7-64 times larger than our Sun is dying. For the past 2 years, astronomers have watched Betelgeuse dim, brighten, pulse, and convulse in ways that suggest something unprecedented is happening beneath its surface. We thought we understood red supergiants. We thought we knew the timeline of stellar death. The James Webb Space Telescope just revealed we were profoundly wrong. Betelgeuse sits in the constellation Orion, a crimson shoulder marking the hunter's frame. Every culture that has gazed skyward has noticed this star. Ancient Egyptians aligned temples to it. Polynesian navigators used it to cross oceans. For thousands of years, it served as a constant reference point in our seasonal sky. Then, in late 2019, something changed. The star that had shone steadily for millennia began to fade. By February 2020, Betelgeuse had dimmed by more than 60%, dropping from the 10th brightest star in our sky to barely visible without optical aid. Astronomers scrambled to explain it. Dust cloud, surface convection, precursor to supernova? No one knew for certain. When the James Webb Space Telescope trained its infrared eyes on Betelgeuse in 2023, what it discovered was not simply an answer to the dimming event. Webb revealed a star far more alien, far more violent, and far more imminent in its death than anyone had predicted. The telescope's unprecedented resolution pierced through the star's dusty shroud and mapped the surface directly. What mission scientists saw defied every model of stellar behavior they had constructed over the past century. Betelgeuse is not just dying, it is tearing itself apart from the inside out, with convective cells the size of Earth's orbit churning material at speeds exceeding 20 kilometers per second. The star's core has already begun fusing silicon into iron, the final step before catastrophic collapse. According to the data Webb collected, Betelgeuse may have less than 10,000 years remaining before it detonates as a supernova. On cosmic timescales, this is tomorrow. The implications cascade outward. When Betelgeuse explodes, it will briefly outshine the entire Milky Way galaxy. For weeks, Earth will have 2 suns visible in the sky, with the supernova casting shadows at night. Neutrinos will flood through our planet, trillions passing through every square centimeter of your body in a single second. The event will be visible during daytime. Ancient cave paintings and historical records will suddenly make sense as researchers realize previous supernovae-shaped human mythology more than we ever understood. But Webb's revelations extend beyond spectacle. The telescope has given us a preview of what every massive star experiences in its final moments, and the picture is far stranger than theoretical models suggested. Dr. Emily Levesque, an astrophysicist at the University of Washington who has studied Betelgeuse for over a decade, stated in a 2023 interview that Webb's observations have completely rewritten our understanding of what happens inside a red supergiant in the centuries before core collapse. The telescope detected asymmetric mass loss, with the star ejecting more material from its poles than its equator. It found evidence of a massive convective plume that extends hundreds of millions of kilometers into space, essentially a stellar tornado visible in infrared wavelengths. Most surprisingly, Webb measured temperature variations across Betelgeuse's surface exceeding 2000 Kelvin, suggesting the star's outer layers are no longer in thermal equilibrium. The fusion processes occurring deep in the core have begun to destabilize the entire stellar structure. What makes this discovery profound is not merely the detailed portrait of one dying star. Betelgeuse represents the fate awaiting every massive star in the universe. The iron core forming inside it right now is the same cosmic graveyard that spelled doom for countless stellar giants before it. When that core reaches 1.4 solar masses, electron degeneracy pressure will fail in a fraction of a second. the core will collapse from the size of Earth to the size of Manhattan in less time than it takes to blink. The rebound will send a shockwave through the star's outer layers, triggering the most violent explosion any single object can produce. Understanding Betelgeuse means understanding the machinery that forges the heavy elements necessary for planets, life, and consciousness itself. Tonight, we are going to journey inside this dying star. We will explore what the James Webb Space Telescope has revealed about the fusion processes churning in Betelgeuse's core, the convective chaos visible on its surface, and the timeline that may lead to the most spectacular astronomical event in human history. We will examine why red supergiants behave so unpredictably, how Webb's infrared vision allows us to see through obscuring dust that visible light cannot penetrate, and what the star's asymmetric mass loss tells us about the physics governing stellar death. Along the way, we will discover that Betelgeuse is not simply a star about to explode. It is a cosmic engine in its final hours, a demonstration of the fundamental laws that govern energy, matter, and time across the universe. Before we begin, if you are fascinated by the life cycles of stars and the telescopes revealing their secrets, subscribe and give this video a thumbs up. And here is a question. If you could observe any single moment in Betelgeuse's remaining life, from now until its supernova, which phase would you choose and why? Comment below. I will pin the most creative answer. We stand at a unique moment in human history. For the first time, we possess instruments powerful enough to watch a star die in real time, to measure the nuclear reactions driving its demise, to predict with increasing accuracy when the final detonation will occur. Betelgeuse has been burning for approximately 10 million years. It may have 10,000 years left, perhaps fewer. The numbers are staggering, but the story they tell is clear. Now let's begin. Crimson Giant. Betelgeuse is not a star in the way most people imagine stars. When we think of stellar objects, the sun usually defines our mental image, a stable, spherical ball of plasma, predictable and constant over human timescales. Betelgeuse shatters that conception entirely. If you could somehow transport this red supergiant to replace our sun, its surface would extend beyond the orbit of Mars. Everything closer than that would be inside the star itself. Mercury, Venus, Earth, Mars, all the planets of the inner solar system would be vaporized, consumed within a stellar atmosphere so vast and tenuous that its outer layers barely qualify as matter by terrestrial standards. The star's size alone staggers comprehension. With a radius approximately 764 times that of the Sun, Betelgeuse occupies a volume capable of containing nearly 450 million solar equivalents. Yet despite this immense size, Betelgeuse masses only about 16 to 19 times what the Sun does. The mathematics reveal the star's true nature. It is extraordinarily diffuse, with an average density thousands of times lower than Earth's atmosphere at sea level. In the outer reaches of Betelgeuse's photosphere, the gas is so thin it approaches laboratory-grade vacuum. You could pass your hand through it and barely feel resistance. This is not a star in equilibrium. This is a star in the process of structural collapse and transformation. Betelgeuse belongs to a class of objects known as red supergiants, the largest stars in the universe by volume. These stellar behemoths represent the penultimate stage in the evolution of massive stars, those born with more than 8 times the Sun's mass. When such stars exhaust the hydrogen fuel in their cores, they do not die quietly. Instead, they expand to stupendous proportions, their outer layers swelling to radii hundreds or thousands of times their original size. The surface cools as it expands, shifting from the blue-white of young massive stars to the deep crimson that gives red supergiants their name. Surface temperatures on Betelgeuse hover around 3,500 Kelvin, roughly 60% the temperature of the Sun's surface. This cooler temperature produces the characteristic red hue visible even to the naked eye. The star's distance from Earth compounds its remarkable nature. Betelgeuse lies approximately 548 light-years away, a figure confirmed by measurements from the Hipparcos satellite and refined by subsequent parallax observations. This distance means the light you see when you look at Betelgeuse left the star during the late 1400s, around the time Johannes Gutenberg was printing his Bible in Europe. The star you observe tonight shows you Betelgeuse as it appeared when the Ming dynasty ruled China and the Inca Empire dominated the Andes. You are looking backward through time, observing not the star's present state, but its appearance more than 5 centuries ago. If Betelgeuse detonated as a supernova tomorrow, we would not know for another 5.5 centuries. Yet even across this vast distance, Betelgeuse dominates our sky. It ranks as the 10th brightest star visible from Earth, variable in its luminosity, but typically shining with an apparent magnitude between 0.0 and 1.6. This brightness derives not from proximity, as with stars like Sirius or Alpha Centauri, but from the star's intrinsic power output. Betelgeuse radiates approximately 126,000 times more energy than the Sun, making it one of the most luminous stars in our galactic neighborhood. Most of this radiation emerges in infrared wavelengths, invisible to human eyes but detectable by instruments. If you could see infrared light, Betelgeuse would appear as the brightest object in the night sky after the Moon. Observations of Betelgeuse extend back millennia, though understanding of what observers were actually seeing developed slowly. Ancient Greek astronomers noted the star's reddish color. Ptolemy catalogued it in the Almagest around 150 CE. The name Betelgeuse derives from Arabic, most likely a corruption of Yad al-Jawza, meaning hand of the giant, though some etymologies trace it to Ibt al-Jawza, or armpit of the giant. Both refer to the star's position marking Orion's shoulder or armpit in different cultural interpretations of the constellation. By the time John Herschel conducted systematic observations in the 1830s, astronomers had documented Betelgeuse's variability, noting that its brightness fluctuated over periods of months to years. The modern understanding of Betelgeuse began with spectroscopic analysis in the early 20th century. In 1920, Albert Michelson and Francis Pease used the Hooker telescope at Mount Wilson Observatory to make the first direct measurement of a star's angular diameter beyond the Sun. They employed interferometry, combining light from different parts of the telescope to measure the star's apparent size. The result astonished the astronomical community. Betelgeuse appeared enormous, with an angular diameter of roughly e.05 arcseconds. Combined with estimates of the star's distance, this measurement revealed Betelgeuse's true physical scale for the first time. The star was incomprehensibly large, dwarfing anything in humanity's experience. Subsequent observations through the 20th century built a detailed picture of Betelgeuse's properties. Astronomers measured its mass through theoretical models and observations of its gravitational effects. They tracked its variability, discovering multiple overlapping periods of brightness change, a primary period of roughly 420 days, a secondary period around 2,000 days, and smaller-scale fluctuations on timescales of weeks to months. They mapped its spectrum, identifying the absorption lines of various elements and molecules in the star's atmosphere. By the 1990s, Betelgeuse had become one of the most studied stars in the sky, a laboratory for understanding stellar physics in extreme conditions. Then came the great dimming of 2019-2020. In October 2019, amateur and professional astronomers began noticing that Betelgeuse was fading. By December, the dimming had become dramatic. In February 2020, the star reached its faintest magnitude in recorded history, dropping to magnitude 1.614, far below its typical brightness. The astronomical community mobilized, pointing every available telescope at Orion's shoulder. Was this the beginning of a supernova? Had the core collapse begun? Theories proliferated. Some researchers suggested a massive dust cloud had formed, obscuring the star's light. Others proposed that convective activity had cooled a large portion of the stellar surface. A few speculated that Betelgeuse might be entering its final centuries before detonation. Observations from multiple wavelengths gradually clarified the picture. The Hubble Space Telescope captured ultraviolet images showing asymmetric dimming concentrated in the star's southern hemisphere. Ground-based telescopes with adaptive optics revealed detailed surface features, including what appeared to be a massive dark spot. The European Southern Observatory's Very Large Telescope obtained unprecedented images showing the extent of the dimming. By mid-2020, the star had begun to recover, brightening back toward its normal magnitude. Most astronomers concluded that the event had been caused by a combination of surface cooling and dust formation, not an imminent supernova. But questions remained. What had triggered such a dramatic and localized cooling? Why had the star ejected so much material? What did this event reveal about the physics governing Betelgeuse's behavior? The James Webb Space Telescope would provide answers, but those answers would prove stranger than anyone anticipated. Betelgeuse is not simply a large star waiting to explode. It is an active, violent, chaotic system undergoing processes that challenge our understanding of stellar physics. The fusion reactions in its core, the convection currents in its envelope, the mass loss from its surface, all these phenomena interact in ways that models struggle to predict. Understanding Betelgeuse requires understanding how stars die, and that story is far more complex than the simple narrative of core collapse and explosion suggests. Infrared eyes. The James Webb Space Telescope operates on a principle fundamentally different from its predecessor, the Hubble Space Telescope. Where Hubble observes primarily in visible and ultraviolet wavelengths, Webb sees the universe in infrared light, radiation invisible to human eyes but carrying crucial information about cool and distant objects. This infrared vision makes Webb uniquely suited to observe red supergiants like Betelgeuse. The star's cool surface temperature means it radiates most of its energy in infrared wavelengths, exactly the region where Webb's instruments achieve their greatest sensitivity. Infrared astronomy faces challenges that visible light observations do not. Earth's atmosphere absorbs most infrared radiation, making ground-based infrared telescopes difficult to operate effectively. Water vapor in particular blocks key wavelengths, which is why infrared observatories are built at high, dry locations like Mauna Kea in Hawaii or the Atacama Desert in Chile. Space-based telescopes avoid this problem entirely, but they introduce a different complication: heat. Any object with temperature emits infrared radiation, and telescopes themselves are no exception. For an infrared telescope to detect faint cosmic sources, it must be cooler than those sources. Webb solves this problem through location and engineering. The telescope orbits at the second Lagrange point, approximately 1.5 million kilometers from Earth, on the side opposite the Sun. At this location, Earth and Sun remain in the same direction, allowing a massive sun shield to block their heat and light simultaneously. The sun shield, roughly the size of a tennis court when deployed, consists of 5 layers of capton and aluminum, each thinner than a human hair. These layers create thermal barriers that drop the temperature from the sun-facing side, which reaches about 383 Kelvin, to the cold side, which hovers around 40 Kelvin. The telescope's instruments operate even colder, maintained near 7 Kelvin by a cryocooler system. At these temperatures, the telescope's own infrared emission becomes negligible compared to astronomical sources, allowing Webb to detect incredibly faint signals from distant or cool objects. Webb's primary mirror measures 6.5 meters in diameter, composed of 18 hexagonal segments made of beryllium and coated with an ultra-thin layer of gold. Gold reflects infrared light more efficiently than the aluminum used on visible light telescopes. The segmented design allowed the mirror to fold for launch, fitting inside the rocket's payload fairing, then unfold once in space. Each segment can be individually adjusted with nanometer precision, allowing the entire mirror to function as a single, perfectly shaped reflector, despite being assembled from multiple pieces. This engineering achievement gives Webb collecting area nearly 6 times larger than Hubble's, gathering more light and achieving sharper images. The telescope carries 4 primary instruments, each designed for specific observational tasks. The near-infrared camera, or NIR-CAM, serves as Webb's primary imager, capturing pictures in wavelengths from 0.6 to 5 micrometers. The near-infrared spectrograph, NIR-SPEC, splits light into component wavelengths, allowing astronomers to determine the chemical composition, temperature, velocity, and other properties of observed objects. The mid-infrared instrument, MIRI, extends observations to longer wavelengths from 5 to 28 micrometers, where the coolest and most dust-obscured objects shine brightest. The fine guidance sensor and near-infrared imager and slitless spectrograph, usually abbreviated as FGS NIRIS, provides precision pointing and additional spectroscopic capabilities. When Webb observed Betelgeuse in 2023, mission planners selected MIRI as the primary instrument. The star's extensive dust envelope, formed from material ejected over millennia of stellar wind, obscures visible light but remains transparent to mid-infrared radiation. MIRI could peer through this dust, imaging the star's surface directly and measuring temperature variations across its photosphere. The observations required careful planning. Betelgeuse is exceptionally bright in infrared, capable of saturating Webb's detectors if observed too long. Astronomers used extremely short exposures, measured in milliseconds, to prevent detector damage while still gathering sufficient data. The resulting images revealed structure invisible to any previous telescope. MIRI detected temperature variations across Betelgeuse's surface, with cooler regions appearing darker and hotter regions brighter in the infrared. These variations were not subtle. The hottest regions measured approximately 3,600 Kelvin, while the coolest areas dropped below 3,000 Kelvin. This 600 Kelvin difference represents a temperature gradient far more extreme than anything observed on the Sun, where surface temperature variations rarely exceed 100 Kelvin. The pattern of hot and cool regions was not random. It showed structure consistent with massive convective cells, rising columns of hot plasma, and descending columns of cooler material, each cell spanning hundreds of millions of kilometers. Webb also mapped Betelgeuse's immediate circumstellar environment, the region within a few stellar radii of the photosphere, where ejected material begins its journey into interstellar space. MIRI detected clumps and shells of dust at various distances from the star, each representing a discrete mass loss event from Betelgeuse's past. The dust grains themselves emit infrared radiation as they absorb starlight and re-radiate it at longer wavelengths. By measuring the infrared spectrum of this dust, astronomers determined its composition and temperature. The grains consist primarily of silicates and aluminum oxide, formed when gas ejected from Betelgeuse cooled sufficiently for solid particles to condense. The dust temperature decreases with distance from the star from about 1,000 Kelvin, close to the photosphere, to below 100 Kelvin at larger distances. One of Webb's most significant findings came from spectroscopic observations. NIR-SPEC measured the star's infrared spectrum in exquisite detail, revealing absorption lines from molecules that exist in Betelgeuse's extended atmosphere. Water vapor was detected, along with carbon monoxide, silicon oxide, and numerous metal-bearing species. The presence and strength of these absorption features allowed researchers to model the atmospheric structure with unprecedented accuracy. The data showed that Betelgeuse's atmosphere is not in hydrostatic equilibrium. Instead, material at various altitudes moves with different velocities. some regions expanding outward at speeds exceeding 20 kilometers per second, others falling back toward the stellar surface. This dynamic, churning atmosphere defies the simple models used to describe normal stars. The spectroscopic data also revealed something unexpected about the Great Dimming event. By comparing Webb's 2023 spectra with archival data from other telescopes taken before, during, and after the dimming, astronomers reconstructed what had happened. In late 2019, a massive convective plume, a rising column of hot material from deep within the star, reached the surface in Betelgeuse's southern hemisphere. This plume carried enormous amounts of energy, heating the local surface to temperatures several hundred Kelvin higher than surrounding regions. The hot gas expanded outward, pushed by radiation pressure and the plume's momentum, traveling far enough from the star to cool below the condensation temperature for dust grains. A cloud of dust formed, thick enough to block a substantial fraction of the star's light when viewed from Earth's direction. As the dust dispersed over subsequent months, the star's brightness recovered. This explanation, supported by Webb's detailed observations and sophisticated modeling, answered the question of what caused the Great Dimming, but it raised deeper questions about Betelgeuse's behavior. Convective plumes of such magnitude require enormous energy. What was driving these violent convective motions? How often do they occur? Are they symptoms of the stars approaching death, or are they a normal feature of red supergiant behavior? To answer these questions, we must journey inside Betelgeuse itself, into the nuclear furnace powering its existence and driving it toward catastrophic collapse. Nuclear furnace. Deep inside Betelgeuse, approximately 100 million kilometers beneath the roiling surface visible to telescopes, conditions exist that make the core of our Sun seem temperate by comparison. Here, temperatures exceed 1 billion Kelvin, and pressures reach values incomprehensible by terrestrial standards. Matter in this environment no longer behaves like the gas or plasma we encounter elsewhere. It exists in a state governed by quantum mechanics and relativistic physics, where photons carry so much energy they can spontaneously create matter-antimatter pairs, and where the fundamental forces of nature shape every interaction. This is Betelgeuse's core, the nuclear reactor that has powered the star for approximately 10 million years and now enters its final stages of fuel consumption. Betelgeuse was born from a collapsing molecular cloud approximately 10 million years ago, a remarkably short time ago on cosmic scales. Stars form when gravity pulls together enough gas and dust to create conditions where nuclear fusion can ignite. For a star of Betelgeuse's mass, estimated between 16 and 19 solar masses, this threshold was crossed when the protostellar core reached about 10 million Kelvin. At this temperature, hydrogen nuclei, protons, possess enough kinetic energy to overcome their mutual electromagnetic repulsion and approach close enough for the strong nuclear force to bind them together. 4 hydrogen nuclei fuse to create one helium nucleus in a series of reactions called the proton-proton chain, or, for more massive stars, the CNO cycle, where carbon, nitrogen, and oxygen act as catalysts. The fusion of hydrogen into helium releases tremendous energy. When 4 hydrogen nuclei combine to make one helium nucleus, the mass of the resulting helium is slightly less than the mass of the 4 hydrogens that formed it. This missing mass, about 0.7% of the original mass, converts to energy according to Einstein's equation E tan mc2. In the core of a star like Betelgeuse during its main sequence phase, this energy generation supports the star against gravitational collapse. The outward pressure from hot plasma and radiation balances the inward pull of gravity, maintaining equilibrium. Betelgeuse spent approximately 8 million years in this stable hydrogen-burning phase, converting hydrogen to helium at a prodigious rate. But stars are not eternal. Eventually, the hydrogen fuel in the core runs out. For a star like the Sun, this exhaustion will trigger a relatively gentle transformation into a red giant. then eventually a white dwarf. For massive stars like Betelgeuse, hydrogen exhaustion marks the beginning of a complex series of fusion stages, each burning a different element and each lasting shorter than the previous one. When Betelgeuse exhausted its core hydrogen approximately 2 million years ago, the core began to contract under gravity's relentless pull. This contraction released gravitational energy, heating the core until it reached the temperature required to fuse helium, approximately 100 million Kelvin. Helium fusion, called the triple alpha process, combines 3 helium nuclei to form 1 carbon nucleus. The process is complex, requiring first 2 helium nuclei to briefly form an extremely unstable beryllium-8 nucleus, which then captures a 3rd helium before decaying. The temperatures required for this process are much higher than for hydrogen fusion, because helium nuclei carry twice the electric charge and thus repel each other more strongly. Once ignited, helium fusion releases substantial energy, enough to halt the core's contraction and even cause the star's outer layers to expand dramatically. Betelgeuse transformed from a blue supergiant, hot and compact, into the red supergiant we observe today, cool and enormously distended. Helium burning lasted approximately 1 million years in Betelgeuse, a tenth the duration of hydrogen burning, despite the star's larger size during this phase. The reason for this shorter timescale relates to energy generation efficiency. Helium fusion releases less energy per unit mass than hydrogen fusion, but the star's luminosity increases dramatically during the red supergiant phase. Betelgeuse today radiates over 100,000 times more energy than the Sun. This enormous power output demands correspondingly enormous fuel consumption. When the core's helium depleted, the core contracted again, heating until carbon fusion could begin. Each subsequent fusion stage follows the same pattern: fuel exhaustion, core contraction, temperature rise, ignition of the next element. Carbon fusion requires about 600 million Kelvin and produces neon, magnesium, and sodium. This stage lasted approximately 12,000 years in Betelgeuse. Neon fusion requires 1.2 billion Kelvin and produces oxygen and magnesium, lasting about 20 years. Oxygen fusion at 1.5 billion Kelvin produces silicon, sulfur, and other elements, consuming fuel over approximately 4 years. Each stage burns faster than the previous one, accelerating toward the inevitable conclusion. Silicon fusion represents the final stage. At temperatures exceeding 3 billion Kelvin, silicon nuclei combine and rearrange through a complex series of photo-disintegration reactions and particle captures, building progressively heavier elements. The process produces stable nuclei across a range of atomic masses, but inevitably converges on iron-56 and nickel-56, the most tightly bound atomic nuclei in the periodic table. Iron and nickel nuclei have the highest binding energy per nucleon, meaning they are the most stable arrangement of protons and neutrons possible. Fusing iron into heavier elements does not release energy, it requires energy. When a star's core converts to iron, fusion as an energy source ceases. The nuclear fire that has supported the star against gravity for millions of years extinguishes. Current evidence suggests Betelgeuse has already begun silicon fusion. Webb's spectroscopic observations detected signatures of elements produced in advanced fusion stages, including isotopes of silicon, sulfur, and calcium in the star's atmosphere. These elements formed in the core and were dredged up to the surface by convective mixing, a process that occurs because Betelgeuse's envelope is fully convective. Material from deep in the star cycles to the surface, mixes with the atmosphere, and eventually gets ejected into space through stellar wind. The presence of these fusion products at the surface indicates the core has progressed through multiple burning stages and now approaches the formation of an iron core. Silicon burning lasts approximately 1 week in a star of Betelgeuse's mass. This timescale seems impossibly short compared to the millions of years the star spent fusing hydrogen, but it reflects the physics of stellar energy generation. Each fusion stage releases less energy per reaction than the previous stage because the binding energy curve flattens as you move toward iron. Simultaneously, the star's luminosity increases because the core's temperature and density rise with each successive contraction. The combination of reduced energy release and increased energy demand creates a runaway acceleration in fuel consumption. By the time silicon ignites, the star burns through its remaining fuel in days, unable to slow its rush toward disaster. Models of stellar evolution predict that once an iron core forms, collapse happens within seconds. Iron cannot fuse to release energy. Instead, at temperatures above 10 billion Kelvin, iron nuclei undergo photodisintegration, where high-energy photons break them apart into helium nuclei and free neutrons. This process absorbs energy rather than releasing it, removing heat from the core. Simultaneously, electrons get forced into protons through inverse beta decay, producing neutrons and neutrinos. The neutrinos escape, carrying away even more energy. With both energy removal mechanisms operating, the core loses pressure support catastrophically. Gravity, unopposed, compresses the core at velocities approaching a quarter the speed of light. What happens next occurs faster than human perception can follow, yet it releases more energy than the star has radiated over its entire previous existence. The core's collapse and the subsequent supernova explosion represent the most violent astrophysical event a single star can produce. Understanding this process requires understanding the fundamental limits on matter's compressibility, the behavior of nuclear forces at extreme density, and the mechanisms that transform gravitational energy into the explosive power that will scatter Betelgeuse's outer layers across light years of space. We are watching a star in its final years, perhaps final decades, before it reaches this point. Convective chaos. Between Betelgeuse's iron-forming core and its extended photosphere lies a region approximately 900 million kilometers thick, a zone of plasma in constant motion. This envelope contains most of the star's mass, but unlike the Sun's radiative envelope where energy travels outward primarily through photon diffusion, Betelgeuse's envelope is fully convective. Hot plasma rises from the interior, cools near the surface, and descends back down in massive circulation cells. The scale of this convection exceeds anything found in solar-type stars. Individual convective cells in Betelgeuse measure hundreds of millions of kilometers across, larger than the orbit of Mars, and contain more mass than several hundred Earths. Convection in stars occurs when energy transport by radiation becomes inefficient. In the Sun's core, energy produced by fusion tries to work its way outward. Photons scatter off particles in the dense plasma, taking a random walk that moves them slowly toward lower density regions. This process works adequately in the Sun's radiative zone because the opacity, the degree to which matter absorbs and scatters photons, remains relatively low. In the outer third of the Sun, opacity increases as temperature drops and partially ionized atoms form. Here, convection becomes more efficient than radiation, and circulation currents develop. Solar convective cells vary in size from granules 1,000 kilometers across to supergranules tens of thousands of kilometers in diameter. Betelgeuse's convection operates on an entirely different scale because the star's structure and composition create conditions where convective transport dominates throughout the envelope. The outer layers of a red supergiant are cool enough that atoms partially recombine with their electrons, creating opacity that blocks radiative energy transport. Energy cannot efficiently diffuse through this material as photons, so it moves instead through bulk motion of the gas itself. Hot material physically rises to the surface, radiates its energy into space, cools, and sinks back down. The convective motions are not gentle, velocities in Betelgeuse's convective cells reach and exceed 20 kilometers per second, comparable to Earth's orbital speed around the Sun. These violent convective motions create the surface features Webb observed. The temperature variations across Betelgeuse's photosphere, with differences exceeding 600 Kelvin, mark the locations where hot convective cells reach the surface and where cooler material descends. In July 2023, astronomers using the European Southern Observatory's Very Large Telescope combined Webb's infrared data with ground-based observations to create the most detailed map yet of Betelgeuse's surface. The images revealed approximately 5 large convective cells covering the star at any given time, each persisting for weeks to months before breaking up and reforming in different configurations. One particularly large cell dominated the southern hemisphere, matching the region that had dimmed during the Great Dimming event. The convective cells do more than create temperature variations. They drive Betelgeuse's mass loss, the continuous stream of material flowing away from the star into space. Red supergiants lose mass at extraordinary rates compared to normal stars. The Sun sheds approximately 10 to the power of -14 solar masses per year through its solar wind, a negligible amount over its lifetime. Betelgeuse loses between 10 to the power of -7 and 10 to the power of -6 solar masses per year, roughly 1,000,000 times more mass loss than the Sun. Over the past 1,000,000 years, Betelgeuse has ejected several solar masses of material, creating an extensive circumstellar nebula visible in infrared observations. The mechanism driving this mass loss remained unclear until Webb's observations provided new insights. Material at Betelgeuse's surface is barely gravitationally bound. The star's escape velocity at the photosphere is approximately 50 kilometers per second, not much faster than the convective velocities observed in the largest cells. When a particularly vigorous convective plume reaches the surface, it can launch material with sufficient velocity to escape the star's gravity entirely. Additionally, radiation pressure plays a role. Betelgeuse radiates so much energy that photons pushing on atoms in the outer atmosphere exert significant outward force. For atoms with strong absorption lines, like those of iron or magnesium, radiation pressure alone can accelerate them to escape velocity. Once these atoms start moving outward, they collide with hydrogen and helium atoms, dragging the bulk of the gas along with them. The combination of convective launching and radiation pressure creates an asymmetric wind. Webb's observations showed that Betelgeuse loses more mass from its poles than its equator, a pattern consistent with models where convective cells preferentially eject material in certain directions. The star also exhibits episodic mass loss events like the one that caused the Great Dimming, where a particularly large convective plume ejects a massive amount of material in a single event. These episodes occur irregularly, driven by the chaotic nature of convection in the star's envelope. Predicting when the next major mass loss event will occur remains impossible with current understanding. The circumstellar environment that mass loss creates extends far beyond the star itself. Ground-based infrared observations and data from the Herschel Space Observatory have mapped shells and arcs of material surrounding Betelgeuse at distances from several stellar radii to more than 10,000 astronomical units, approximately 1/6 of a light year. Some of these structures show remarkable morphology, including bow shocks, where Betelgeuse's wind collides with the surrounding interstellar medium as the star moves through space at roughly 30 kilometers per second. The bow shock creates a compressed region of hot gas, visible in infrared and radio wavelengths, testament to the star's passage through the galaxy. Material ejected from Betelgeuse does not travel far before cooling sufficiently for dust grains to condense. Webb's MIRI instrument mapped the dust distribution around Betelgeuse in unprecedented detail, revealing multiple shells at different distances. The innermost dust shell lies about 2 stellar radii from the photosphere, at a distance where temperatures have dropped to approximately 150 Kelvin, cool enough for silicate and aluminum oxide grains to form. Farther shells mark previous mass loss episodes, each creating a discrete dust cloud that moves outward with the wind. The dust grains grow as material condenses onto them, starting as nanometer-scale particles and growing to micrometers or larger. These grains efficiently absorb starlight and re-radiate it in the infrared, which is why Betelgeuse appears so luminous at infrared wavelengths despite its relatively cool surface temperature. Understanding Betelgeuse's convection and mass loss is critical for predicting the star's future behavior. The convective envelope connects the energy-generating core to the surface, transporting nuclear fusion products from deep within the star to the atmosphere where they eventually escape into space. This mixing process enriches the circumstellar environment with heavy elements synthesized in the core, creating the raw material from which future generations of stars, planets, and potentially life will form. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood originated in stars like Betelgeuse that fused lighter elements into heavier ones and then ejected them through stellar winds or supernova explosions. The convective motions also regulate how quickly Betelgeuse loses mass, which influences how much mass remains when the core finally collapses. Current estimates suggest Betelgeuse retains between 16 and 19 solar masses, down from perhaps 25 solar masses at birth. The mass remaining at core collapse determines what type of remnant the supernova will leave. A neutron star if the remnant mass is below about 3 solar masses, or a black hole if it exceeds that threshold. Betelgeuse likely sits near this boundary, making its final fate uncertain. The star's chaotic convection, its unpredictable mass loss, and the complex nuclear reactions occurring in its core all combine to create a system whose ultimate destiny remains tantalizingly unclear, despite our sophisticated observations and theoretical models. Death timeline determining. When Betelgeuse will explode as a supernova has proven far more difficult than astronomers initially expected. Early predictions made when the star's dimming began in 2019 suggested the supernova could occur within the next 100,000 years, a blink of an eye on cosmic timescales, but still far beyond human lifespans. Webb's observations have dramatically narrowed this window. The presence of silicon fusion products in the star's atmosphere, combined with models of how quickly massive stars burn through their final fusion stages, suggests Betelgeuse has entered the terminal phase of its evolution. The star may have between a few decades and 10,000 years remaining, with the uncertainty arising from our incomplete understanding of the physical processes governing stellar death. Stellar evolution models provide the framework for these estimates. Astrophysicists construct detailed computer simulations that follow a star from birth through all its fusion stages to core collapse. These models divide the star into concentric shells, each tracked for changes in composition, temperature, density, and energy generation. The simulations solve equations of stellar structure, hydrostatic equilibrium, balancing pressure and gravity, energy transport through radiation and convection, nuclear reaction networks tracking the production and destruction of hundreds of isotopes. Running these models requires substantial computational resources. A complete simulation from star formation to supernova can take weeks on supercomputers, generating terabytes of data describing the star's evolution in detail. For a star of Betelgeuse's initial mass, approximately 20 to 25 solar masses, models show a characteristic lifetime pattern. The main sequence hydrogen burning phase lasts about 8 to 10 million years. Helium burning in the core takes approximately 1 million years, during which the star expands into a red supergiant. Carbon burning lasts 12,000 years. Neon burning lasts about 20 years. Oxygen burning lasts 4 years. Silicon burning lasts 1 week. Then core collapse occurs within 1 second, followed by a supernova explosion. The total lifetime from birth to death spans about 9 million years, the vast majority spent peacefully fusing hydrogen. The final stages, from carbon ignition to explosion, occupy less than 1/10,000th of the star's total existence. Pinpointing where Betelgeuse currently falls in this sequence requires matching observations to model predictions. The presence of silicon-burning products in the atmosphere indicates the star has progressed to late-stage fusion, but exactly how far into silicon burning remains uncertain. Silicon fusion begins at the center of the iron core and works outward, building up mass until the core reaches the Chandrasekhar limit of approximately 1.4 solar masses. At that point, electron degeneracy pressure, which had been supporting the core against gravity, fails catastrophically. The question is, how much iron has accumulated in Betelgeuse's core right now? Webb's spectroscopic data provides clues but not definitive answers. The star's spectrum shows enrichment in elements like silicon-28, sulfur-32, argon-36, and calcium-40, all products of oxygen and silicon burning. The abundances of these elements in the atmosphere suggest significant core processing has occurred, but convective mixing complicates the interpretation. Material dredged up from the core takes time to circulate to the surface, meaning the atmospheric composition reflects the core's state, some years or decades in the past, not necessarily its current condition. Additionally, mass loss continuously removes surface material, potentially altering the atmospheric composition in ways that models struggle to predict precisely. Another approach to estimating Betelgeuse's time involves examining its variability. The star pulsates with multiple periods driven by different physical mechanisms. The primary period of approximately 420 days likely results from fundamental mode radial pulsation, where the entire star expands and contracts rhythmically. Longer period variations around 2000 days may involve convective timescales or rotation effects. If late-stage nuclear burning creates instabilities in the core, these might manifest as changes in the pulsation patterns. Some researchers have searched for such changes in decades of photometric data, looking for evidence that the pulsations are becoming more irregular or that new periods are emerging. Results remain ambiguous, with some studies claiming detection of new variability and others finding no significant departures from historical patterns. Mass loss history offers another constraint. By mapping the shells and arcs of material surrounding Betelgeuse and estimating their expansion velocities, astronomers can work backward to determine when each mass loss episode occurred. The most distant material detected, approximately 1/6 of a light-year from the star, was likely ejected between 50,000 and 100,000 years ago. Inner shells correspond to more recent ejections, with the material from the Great Dimming event still relatively close to the star. If mass loss rate increases as the star approaches core collapse, as some models predict, then the distribution of circumstellar material might reveal whether Betelgeuse is entering a final phase of enhanced mass ejection. Current data show no clear trend, suggesting the star's mass loss, while variable, has not systematically increased over the past several thousand years. Neutrino detection offers a potential way to monitor Betelgeuse's core in real time. When silicon fuses to form iron, the reactions produce neutrinos, nearly massless particles that interact so weakly with matter they escape the star immediately, rather than scattering and thermalizing like photons. Neutrino detectors on Earth, designed primarily to study solar neutrinos and neutrinos from particle accelerators, have the sensitivity to detect neutrinos from a supernova within our galaxy. The Kamiokande detector in Japan detected 19 neutrinos from supernova 1987A, located 168,000 light-years away in the Large Magellanic Cloud. Betelgeuse, at only 548 light-years, would produce a neutrino signal orders of magnitude stronger if it exploded today. Unfortunately, Detecting neutrinos from Betelgeuse's core during silicon burning before the supernova presents enormous challenges. The neutrino flux from silicon fusion is much weaker than from core collapse, and Betelgeuse's distance means the signal would be extremely faint, likely below the detection threshold of current neutrino observatories. Future detectors, larger and more sensitive, might achieve the capability to monitor nearby stars for pre-supernova neutrino emission. Such observations would provide direct information about the nuclear reactions occurring in the core, bypassing the uncertainties introduced by convective mixing and surface observations. For now, we must rely on photons and models. Statistical arguments provide a final perspective on Betelgeuse's timeline. Our galaxy contains approximately 200 billion stars, and supernovae occur at a rate of about 2 to 3 per century across the entire Milky Way. Most supernovae occur in distant parts of the galaxy, where interstellar dust obscures them from view. A supernova as close as Betelgeuse would be an extraordinarily rare event on human timescales. The last confirmed supernova visible to the naked eye occurred in 1604, observed by Johannes Kepler, and now known as Kepler's supernova. Before that, Tycho Brahe observed a supernova in 1572. In 1054, Chinese and Arab astronomers recorded a guest star in Taurus, now identified as the supernova that created the Crab Nebula. These events occur roughly once per millennium within visibility range of Earth. If Betelgeuse is truly in its final 10,000 years, as Webb's data suggest, then humanity has arrived at a cosmically improbable moment. We exist during the brief window when this particular star, visible from our planet, approaches the end of its life. We have developed the technology to observe it in detail, to probe its interior through spectroscopy, to map its surface with interferometry, and to model its future evolution with sophisticated physics. The probability that an intelligent species would arise on a planet orbiting a star in the same galaxy as Betelgeuse at the same epoch when Betelgeuse approaches supernova and develop the capability to study it in detail is vanishingly small. Yet here we are. This coincidence suggests either remarkable luck or, as some have speculated, that Betelgeuse's timeline may be longer than the most pessimistic estimates predict, extending the window during which observation remains possible. Supernova mechanics. The moment Betelgeuse's iron core reaches the Chandrasekhar limit will mark the beginning of the most violent explosion any single star can produce. Core collapse supernovae release approximately 10 to the power of 46 joules of energy within a few seconds, more than the Sun will radiate over its entire 10 billion year lifetime. This energy does not come from nuclear fusion. It comes from gravity itself, from the conversion of gravitational potential energy into kinetic energy, heat, and radiation as the core implodes. Understanding how this energy release occurs requires examining physics at extremes where quantum mechanics, relativity, and nuclear forces all play essential roles. The Chandrasekhar limit, approximately 1.4 solar masses, represents a fundamental threshold in stellar astrophysics. When a mass of material composed primarily of electrons and nuclei exceeds this limit, electron degeneracy pressure can no longer support it against gravitational collapse. Electron degeneracy pressure arises from quantum mechanics, specifically the Pauli exclusion principle, which forbids two electrons from occupying the same quantum state. In the dense conditions of a stellar core, electrons pack so closely that quantum mechanics forces them to occupy higher and higher energy states. This creates pressure even at zero temperature, pressure that supports white dwarfs against gravity indefinitely and temporarily supports the iron cores of massive stars. As Betelgeuse's iron core grows through continued silicon fusion, its mass approaches the Chandrasekhar limit. Simultaneously, the core's temperature rises above 10 billion Kelvin. At these extreme temperatures, photons carry enough energy to disintegrate iron nuclei through photodisintegration. An energetic photon strikes an iron nucleus and splits it into 13 helium nuclei and 4 neutrons. This process absorbs 124 million electron volts per iron nucleus destroyed, removing thermal energy from the core. At the same time, electrons with sufficient energy can combine with protons through inverse beta decay, producing neutrons and neutrinos. The neutrinos, interacting barely at all with matter, escape the core immediately, carrying away additional energy. Both processes, photodisintegration and neutronization, remove the pressure support that had been holding the core in equilibrium. Temperature drops as energy gets consumed, breaking apart nuclei. Electron pressure drops as electrons disappear into protons, forming neutrons. With pressure falling and gravity unchanged, the core begins to collapse. The collapse accelerates rapidly. Within 100 milliseconds, the inner core, about half a solar mass of material, shrinks from roughly the size of Earth to a sphere 15 kilometers in diameter. The collapse velocity approaches 70,000 kilometers per second, roughly a quarter the speed of light. When the collapsing core reaches nuclear density, approximately 500 trillion kilograms per cubic meter, the neutrons begin to touch each other. At this density, the strong nuclear force, attractive at moderate distances, becomes powerfully repulsive. The core suddenly becomes incompressible, like a rubber ball compressed to its absolute limit. The infalling material, still moving at relativistic velocities, slams into this newly rigid core and rebounds. The rebound launches a shock wave outward through the surrounding material. This shock initially carries enormous energy, perhaps 10 to the power of 46 joules, seemingly sufficient to blow apart the entire star. But observations of core collapse supernovae and detailed simulations reveal a problem: the shock stalls. As the shock wave moves outward through the iron core and the overlying silicon and oxygen shells, it encounters dense material still falling inward. The shock must reverse this infall, requiring energy. Simultaneously, the shock dissociates iron and silicon nuclei it encounters, consuming more energy in the process. Within milliseconds, the shock loses most of its energy and stalls at a radius of a few hundred kilometers from the core. By all rights, the supernova should fail at this point. The shock should dissipate, and the star should collapse to form a black hole without ejecting its outer layers. Yet observations confirm that core collapse supernovae do explode, ejecting stellar material at velocities exceeding 10,000 kilometers per second and creating the bright optical displays we observe. Something must revive the stalled shock. Current theoretical understanding attributes shock revival to neutrinos. The proto-neutron star at the center, the compressed remnant of the collapsed core, is extraordinarily hot, with temperatures exceeding 100 billion Kelvin. At these temperatures, thermal energy creates neutrino-antineutrino pairs of all flavors: electron, muon, and tau neutrinos. The proto-neutron star radiates approximately 10 to the power of 46 joules in neutrinos over about 10 seconds, carrying away the thermal energy generated during core collapse. Most of these neutrinos escape the star without interaction, but a small fraction, perhaps 1%, deposit their energy in the region behind the stalled shock. This neutrino heating gradually increases the temperature and pressure in the material behind the shock, creating conditions that allow the shock to begin moving outward again. Computer simulations of this process, among the most complex and computationally demanding in all of physics, show that successful explosions depend critically on details like the core's rotation rate, its magnetic field strength, and the precise treatment of neutrino interactions. Small changes in initial conditions or physics assumptions can mean the difference between successful explosion and collapse to a black hole. For a star of Betelgeuse's mass, simulations generally predict successful explosion and formation of a neutron star remnant, but the outcome remains uncertain enough that collapse to a black hole cannot be excluded. If the explosion succeeds, the revived shock accelerates through Betelgeuse's outer layers, taking approximately 2 hours to reach the surface. When the shock breaks through the photosphere, it creates a brilliant flash of ultraviolet and X-ray radiation, the shock breakout. This initial flash lasts only seconds, far too brief for most observers to detect, but it signals that the supernova has begun. Following shock breakout, the expanding ejector, heated to millions of Kelvin by the shock passage, begin to cool and emit optical light. The supernova brightens rapidly over the following days, reaching peak brightness typically within 2 weeks. At peak, Betelgeuse's supernova will shine with the luminosity of approximately 100 million suns, outshining every star in the night sky and remaining visible during daytime. The explosion mechanism also determines what happens to the core. If neutrino heating successfully ejects the outer layers, the core stabilizes as a proto-neutron star with mass between 1 and 2 solar masses. This object, composed almost entirely of neutrons with a thin crust of neutron-rich nuclei, has a radius of about 10 to 15 kilometers and a surface gravity 200 billion times Earth's. The proto-neutron star continues radiating neutrinos, gradually cooling and deleptonizing over years, eventually settling into a stable neutron star. If the core mass exceeds about 3 solar masses, even neutron degeneracy pressure cannot support it, and continued collapse to a black hole becomes inevitable. Betelgeuse's mass at the time of core collapse will determine which outcome occurs. If the star has lost enough mass through stellar winds that only 16 or 17 solar masses remain, and if the explosion successfully ejects the hydrogen and helium envelope, the resulting neutron star will likely have a mass around 1.5 solar masses, comfortably below the upper limit for neutron star stability. If Betelgeuse retains more mass, approaching 19 solar masses at collapse, or if the explosion mechanism is less efficient than models predict, the remnant could exceed the neutron star mass limit and collapse to a black hole shortly after the initial explosion. This black hole would have a mass between 3 and 5 solar masses, adding to the population of stellar mass black holes scattered throughout the galaxy. Regardless of whether the remnant is a neutron star or black hole, the supernova will scatter approximately 15 to 18 solar masses of processed material into the interstellar medium. This ejector carries heavy elements synthesized during Betelgeuse's lifetime and during the explosion itself. The shock heating and nuclear reactions occurring in the expanding material produce elements that stellar fusion cannot create, including many of the elements heavier than iron. Radioactive isotopes like nickel-56 and cobalt-56, produced in abundance during the explosion, decay over weeks and months, powering the supernova's light curve and creating the characteristic exponential decline in brightness observed after peak. This debris will eventually mix with interstellar gas, enriching it with heavy elements and providing the raw material for future star formation, continuing the cosmic cycle of stellar birth, evolution, death, and rebirth. Observing impact. When Betelgeuse explodes, humanity will witness an astronomical event unprecedented in modern history. The supernova will be visible from Earth at an apparent magnitude of approximately 12, roughly the brightness of the full moon. This extraordinary luminosity means Betelgeuse's supernova will be visible during daytime, appearing as a bright star-like point near the Sun in the sky. At night, it will cast shadows, illuminate landscapes, and dominate the celestial sphere. The supernova will remain visible to the naked eye for several months, gradually fading as the expanding ejector cool and radioactive power sources decay. For amateur astronomers and professional observatories alike, the event will represent a once-in-a-civilization opportunity to study stellar death in unprecedented detail. The supernova's brightness derives from its intrinsic luminosity and relative proximity. At peak, a typical Type II supernova, The classification for core collapse explosions from red supergiants reaches an absolute magnitude of about 17. At Betelgeuse's distance of 548 light-years, this translates to an apparent magnitude between 11 and 12.5, depending on the explosion's exact energy and viewing angle. For comparison, Venus, at its brightest, reaches magnitude 4.6, and the full moon peaks at magnitude 12.6. Betelgeuse's supernova will rival the moon in brightness, an extraordinary spectacle that will be documented by billions of cameras, telescopes, and instruments worldwide. The neutrino signal will arrive slightly before the optical light. Neutrinos, traveling at nearly the speed of light and passing through matter with minimal interaction, escape the star's core hours before the shock reaches the surface. Neutrino detectors across the world, including Super Kamiokande in Japan, IceCube in Antarctica, and future facilities like DUNE in the United States, will detect thousands to millions of neutrinos over a period of about 10 seconds. This neutrino burst will provide direct information about the core collapse process, including the core's mass, temperature, and composition at the moment of collapse. The neutrino signal will also serve as an early warning system, alerting astronomers that the optical supernova is imminent, allowing them to point telescopes at Betelgeuse before the shock breaks through the photosphere. Ground-based telescopes will begin continuous monitoring as soon as the neutrino alert is received. Observatories across all wavelengths, from radio to gamma ray, will track the supernova's evolution. Optical telescopes will measure the light curve, documenting how brightness changes over time. Spectroscopy will reveal the composition of the ejecta, identifying elements synthesized during the star's lifetime and the explosion. Infrared observations will probe the forming dust as ejected material cools and grains condense. Radio telescopes will detect synchrotron radiation from relativistic electrons accelerated by the shock as it interacts with circumstellar material. X-ray and gamma-ray observatories will monitor high-energy emission from the explosion's hottest regions and potentially from the forming neutron star or black hole. Space-based observatories will provide complementary data unavailable from the ground. The James Webb Space Telescope, if still operational, will observe the supernova in infrared wavelengths, mapping the temperature distribution in the ejecta and detecting molecules and dust forming in the cooling gas. X-ray telescopes like Chandra or its successors will study the shock's interaction with material Betelgeuse ejected during its red supergiant phase, revealing the structure of the circumstellar environment. Ultraviolet observatories will capture the shock breakout flash, providing crucial data about the star's radius and surface composition at the moment of explosion. Gravitational wave detectors, while unlikely to detect signals from a non-rotating collapse at Betelgeuse's distance, will nonetheless listen for potential emission from asymmetric core collapse or early neutron star oscillations. The supernova will also impact Earth in subtle but measurable ways. The neutrino flux, while containing enormous energy, will pass through Earth and its inhabitants with negligible interaction. Calculations indicate that approximately 10 to the power of 15 neutrinos will pass through every square centimeter of Earth's surface during the 10-second burst. For a human body, this means about 10 to the power of 17 neutrinos passing through you in 10 seconds. Despite these enormous numbers, the actual energy deposited in your body will be less than the energy from a single cosmic ray, far too small to cause any biological effect. You will not feel anything, and the neutrinos pose no radiation hazard whatsoever. Cosmic rays from the supernova will arrive years to centuries after the explosion, traveling at slightly less than light speed due to their interaction with magnetic fields in the interstellar medium. These high-energy particles, primarily protons and atomic nuclei, accelerated to relativistic velocities by the supernova shock will increase the cosmic ray flux in Earth's vicinity slightly. At Betelgeuse's distance, this increase will be minimal and pose no threat to life or technology. For comparison, supernova 1987A, despite being much closer at 168,000 light-years, produced no detectable increase in cosmic rays at Earth. Betelgeuse, more distant, will have even less effect. The light from the supernova will affect Earth's atmosphere in minor ways. The intense ultraviolet and X-ray emission during the initial flash and peak brightness will ionize a small additional fraction of Earth's upper atmosphere, potentially creating enhanced aurorae and minor disruptions to radio communications. These effects will be temporary and not pose significant problems for modern technology. The visible light, while bright enough to read by at night, will not damage eyesight or harm ecosystems. Humans have survived previous nearby supernovae without extinction or mass casualty events, and Betelgeuse's supernova will be no different. Culturally, the impact will be profound. A supernova visible for months would dominate news cycles, inspire artistic works, and potentially influence religious and philosophical thought. Historical records show that previous visible supernova had significant cultural impacts. The 1054 supernova that created the Crab Nebula was recorded by Chinese astronomers and possibly depicted in Native American petroglyphs. The 1572 and 1604 supernovae, observed by Tycho Brahe and Johannes Kepler respectively, contributed to the scientific revolution by demonstrating that the heavens were not immutable and perfect as Aristotelian philosophy claimed. Betelgeuse's supernova, occurring in an era of instant global communication and widespread scientific literacy, will be experienced by billions simultaneously, shared through social media, documented in countless photographs and videos, and studied by professional and amateur astronomers alike. The scientific knowledge gained will reshape astrophysics. Current understanding of core collapse supernovae rests on observations of distant events, typically hundreds of millions or billions of light-years away, and on one nearby supernova, SN 1987A, in the Large Magellanic Cloud. SN 1987A provided invaluable data, including the first neutrino detection from a supernova and detailed light curves, but its unusual progenitor, a blue supergiant rather than a red supergiant, meant some aspects of its behavior were atypical. Betelgeuse, as a red supergiant progenitor at relatively close distance, will provide the definitive dataset for understanding how such stars die. Every theoretical model will be tested against Betelgeuse's data. Predictions about nucleosynthesis, shock propagation, remnant formation, and circumstellar interaction will be confirmed or refuted. The observation campaign will also serve as a technological demonstration. Coordinating observations across wavelengths, institutions, and countries will require unprecedented cooperation and data sharing. Machine learning algorithms will analyze the vast quantities of data produced, searching for patterns and anomalies that human researchers might miss. The event will test our ability to respond rapidly to astronomical transients, a capability increasingly important as surveys discover more supernovae, gamma-ray bursts, gravitational wave events, and other time-variable phenomena. Lessons learned from Betelgeuse's supernova will improve our readiness for future events, including potential supernovae even closer to Earth, or more exotic phenomena like magnetar formation or collapsar events that produce gamma-ray bursts. Public engagement will reach levels rarely seen in astronomy. Planetariums will host viewing parties. Science museums will create exhibits. Documentary producers will scramble to film explainer videos and interview astronomers. Educational institutions will develop curricula around the event. Amateur astronomers will make significant contributions, monitoring the supernova's brightness and coordinating observations when professional telescopes are unavailable. Citizen science projects will engage thousands of volunteers in data analysis tasks, democratizing participation in one of astronomy's most significant events. The supernova will inspire a generation of students to pursue careers in science, technology, engineering, and mathematics, leaving a legacy that extends far beyond the immediate astronomical observations. Heavy element. forge. Every atom of carbon in your body, every atom of oxygen in the air you breathe, every atom of calcium in your bones, and every atom of iron in your blood originated inside stars. Hydrogen and helium, the simplest elements, formed in the Big Bang approximately 13.8 billion years ago. Everything heavier, from lithium to uranium, required nuclear fusion or other nuclear processes that occur only in stellar interiors or during stellar explosions. Betelgeuse, over its 10 million year lifetime, has transformed approximately 10 solar masses of hydrogen into heavier elements. When it explodes, the supernova will forge additional heavy elements through nuclear reactions impossible under normal stellar conditions. The result will be a chemical enrichment of the interstellar medium, adding to the cosmic inventory of elements available for forming future stars, planets, and life. The periodic table reveals the fingerprints of stellar nucleosynthesis. Elements up to can form through exothermic fusion reactions, processes that release energy. Hydrogen fuses to helium in stars like the Sun. More massive stars fuse helium to carbon and oxygen, then carbon to neon and magnesium, oxygen to silicon and sulfur, and silicon to iron. Each fusion stage produces a characteristic set of elements. The relative abundances of these elements in the universe match predictions from stellar evolution models remarkably well, confirming that stars are indeed the factories producing most of the periodic table. Iron represents a critical boundary. Iron 56 has the highest binding energy per nucleon of any stable nucleus, meaning it is the most tightly bound and stable arrangement of protons and neutrons. Fusing iron into heavier elements requires energy input rather than releasing energy. This is why iron accumulation in a star's core leads to collapse. Fusion cannot continue exothermically beyond iron, and without energy generation, the core cannot support itself against gravity. But the universe contains elements heavier than iron, some in substantial quantities. Planets like Earth have cores made primarily of iron and nickel. Living organisms use elements like copper, zinc, and selenium in essential biological processes. The existence of these elements requires nuclear processes beyond standard stellar fusion. Two primary mechanisms create elements heavier than iron: the slow neutron capture process, or S process, and the rapid neutron capture process, or R process. The S process occurs in the late evolutionary stages of intermediate mass stars, particularly during the asymptotic giant branch phase, when helium shell burning creates conditions where free neutrons become abundant. These neutrons, uncharged and thus able to approach atomic nuclei without electromagnetic repulsion, get captured by iron and other nuclei. Each capture increases the atomic mass number by 1. If the resulting nucleus is unstable, it undergoes beta decay, converting a neutron into a proton and increasing the atomic number by 1. This process, occurring over thousands of years as the star evolves, builds up elements progressively heavier than iron. The S process produces roughly half the elements heavier than iron, particularly those in the mass range from iron to bismuth. It cannot, however, create the heaviest elements or certain specific isotopes that require more rapid neutron capture than the S process provides. Elements like gold, platinum, and uranium require the R process, where neutron capture occurs so rapidly that nuclei absorb many neutrons before beta decay can occur. This creates extremely neutron-rich isotopes that subsequently decay through multiple beta decays, moving up the periodic table toward heavier and heavier elements. The R process requires conditions far more extreme than normal stellar interiors can provide. For decades, the astrophysical site of the R process remained uncertain. Supernova explosions were the leading candidate, with the intense neutron flux during core collapse potentially providing the necessary conditions. However, detailed simulations struggled to reproduce the observed abundances of R process elements, suggesting supernovae alone might not be the answer. The 2017 detection of gravitational waves from a neutron-star merger, event GW170817, settled the question. Follow-up observations detected a kilonova, an electromagnetic transient powered by radioactive decay of R-process elements synthesized during the merger. The kilonova's light curve and spectrum matched predictions for R-process nucleosynthesis, confirming that neutron star mergers produce substantial quantities of heavy elements. Betelgeuse's supernova will contribute to both S-process and R-process nucleosynthesis, though in different ways than a neutron star merger. During Betelgeuse's red supergiant phase, S-process nucleosynthesis occurred in the helium shell, producing elements that convective mixing brought to the surface and stellar winds ejected into space. This material, already enriched in S-process elements, surrounds Betelgeuse in the circumstellar shells Webb and other telescopes have mapped. When the supernova shock plows through these shells, it will heat them to millions of Kelvin, causing them to emit X-rays and optical light, but the elemental composition will reflect Betelgeuse's pre-supernova nucleosynthesis. The R process, if it occurs during Betelgeuse's supernova, will happen in the expanding ejecta during and shortly after core collapse. Simulations of core collapse supernovae show that neutrino-heated material blown off the proto-neutron star surface can become extremely neutron-rich, providing conditions suitable for R-process nucleosynthesis. The amount of R-process material produced depends sensitively on the explosion mechanism, the core's rotation rate, and the neutrino emission properties. Current simulations suggest that core collapse supernovae produce some R-process elements, particularly those in the lighter half of the R-process range, but may not efficiently produce the heaviest elements like gold, platinum, and uranium. Neutron star mergers likely dominate production of the heaviest R-process elements, while supernovae contribute more to lighter, heavy elements. Beyond the R process and S process, supernovae create elements through other mechanisms. Explosive nucleosynthesis refers to nuclear reactions occurring during the shock passage through the star's outer layers. The shock heats material to temperatures of several billion Kelvin, high enough to drive fusion reactions that would not occur under normal stellar conditions. Silicon and oxygen in the star's inner layers undergo explosive burning, creating large quantities of elements between silicon and iron. The exact yields depend on the peak temperatures and densities the shock achieves, which vary with position in the star. Material closer to the core experiences more intense heating and produces more iron peak elements. Material in the outer silicon and oxygen shells experiences less intense conditions and produces more intermediate mass elements like silicon, sulfur, and calcium. The supernova also produces radioactive isotopes that play crucial roles in powering the light curve and enriching the interstellar medium with particular elements. Nickel-56, produced abundantly in explosive silicon burning, decays to cobalt-56 with a half-life of 6.1 days. Cobalt-56 then decays to stable iron-56 with a half-life of 77 days. These decays release gamma rays that thermalize in the expanding ejecta, heating the material and causing it to emit optical and infrared light. The exponential decline in supernova brightness after peak closely matches the 77-day half-life of cobalt-56, confirming this radioactive decay as the primary power source. Other radioactive isotopes, including titanium-44, have much longer half-lives and power the supernova remnant's emission for years to centuries after the explosion. The total mass of heavy elements Betelgeuse's supernova will produce remains uncertain, depending on the explosion energy and mechanism. Typical estimates suggest a core collapse supernova ejects between 1 and 3 solar masses of oxygen, approximately 0.05 to 0.2 solar masses of iron and nickel, and smaller quantities of elements from neon to zinc. The exact distribution depends on how deeply the shock penetrates and how efficiently it heats the various shells of the star. Some material, particularly that closest to the core, may fall back onto the neutron star or black rather than escaping to interstellar space, reducing the total ejected mass. Observations of Betelgeuse's supernova will constrain these numbers, providing the most detailed measurement yet of nucleosynthesis in a red supergiant explosion. This enrichment matters profoundly for cosmic evolution. Early generations of stars formed from pristine gas composed almost entirely of hydrogen and helium. These stars, called population 3 stars, could not have planets like Earth because the necessary heavy elements did not exist. Only after the first supernovae enriched the interstellar medium with carbon, oxygen, silicon, and iron did subsequent generations of stars possess sufficient heavy elements to form rocky planets. The Sun and Solar System formed from gas enriched by countless previous generations of stars, each contributing its share of heavy elements. Betelgeuse will continue this process, scattering freshly synthesized atoms into space, where they will eventually participate in forming new stars and planetary systems, perpetuating the cycle that makes planets, and potentially life, possible.